This is lesson number 4, Input-Output Programming in C#. Input-output devices. We know there are a number of input-output devices in the real world which we actually work with every day. For example, for input devices are the keyboard and the mouse, and output devices which come to mind immediately are the screen, the printer, and the file system. In I/O programming, we actually need to interact with these devices. This is what makes programming I/O a little bit more complex than it would otherwise seem to be. Well, it's not complex, which we will see now. Different input-output devices behave differently in different platforms and systems. For example, the mouse interface which you're currently using for the Windows operating system is definitely different than the mouse interface for the Linux systems. Do we as programmers need to worry about all these fine details of how the various device drivers work on different operating systems? No. The C# language provides us the beautiful abstraction called streams. Since we have input devices and output devices, there are two types of streams, input stream and output stream. And C# encourages us to use streams. It's deserved to remind that the programs we write in C# are actually compiled to intermediate language, which is then executed by the common language runtime. The common language runtime takes care of the fine details of actually interacting with the hardware using the respective native device drivers. So, if we use streams, we are absolved of the worry of having to deal with different diverse nature of the hardware. A stream is an abstraction that represents an input or an output device. And what is an abstraction? An abstraction is like a black box. What is inside the black box? We do not know. It is always debatable. So they say it is best left to itself. Similarly, C# streams is an abstraction. The C# language handles all the fine details of the various input-output devices, freeing us, the programmer, to concentrate on the real problem-solving application and not worry about the hardware. Let us look at the file system. The file system is the heart of the input-output environment. We know the data is always represented as bits and bytes. It is the file system that organizes the data, provides a name for it, provides a storage and retrieval mechanism based on the file name and the file path, and provides actual meaning for the data. These files and the directories which both comprise the file system are abstracted by classes in the .NET framework. For example, to work with directories, the directory class gives us static methods for creating, moving, exploring directories. For example, there is a create directory method which will create a directory for you. Get directories gets all the named directories from a given path. Get logical drives, get files, get parent, and there's even a move method which moves the directory and its contents to a different path. Working with files. A file class is used for the file operations such as creating, copying, moving, deleting, or appending to files. Some of the methods on the file class are create, copy, delete, open read and open write, which gives us a stream on the file for reading and writing, and create text and append text, which helps us to write text to a new file or append text to an existing file. Now that we looked at file systems, let's look at file streams. To read a file, we need an input stream, and to write to a file, we need an output stream. The open read and open write methods in the file class provide us a stream for reading and writing to files. For example, here we have two streams, input stream and output stream. We got the input stream by using the open read, and the output stream using the open write. Remember, input stream and output streams are variables in our program. So let us look at a simple example of copying a file. Here is a file copy program. First of all, we need a source file and a destination file. So on the source file, we open the input stream, and to the destination file, we open an output stream. We then define a byte array. The input stream has a method called read, which read bytes from the input stream into the byte array. As and when we read the bytes into the byte array, we write the contents of the byte array to the output stream using the write method. And finally, remember to always close the input stream and the output stream when you're done using the close method. This is a very simple example. Here, in the example, we read a file called the source. The input stream class has a method called read. This will read the contents of the file to a byte array, and the read method also returns number of bytes that is read from the stream. The output stream has a write method where we write the contents of the byte array to the underlying file system. And how do we know the end of the file is reached? The end of the file is understood to be reached when 0 bytes are read from the stream. Let's see a quick demo here. Let me bring up Visual Studio. Okay. Here is an example to copy a file. We have a method called copy file, which takes a from value, which is source, and to value, which is destination. What we do is we open an input stream and output stream using the file open read and open write method. We then declare a byte array called buffer. We read the contents of the source into the buffer, and we write the buffer to the output stream. We keep on reading from the input stream till the bytes read is equal to 0. Bytes read equal to 0 denotes the end of the file. So until end of the file is reached, whatever we read into the byte array called buffer, we write to the output stream. And that is how we copy a file. If you look at this example here, we have a try and a catch block. So it is always a good practice to use try and catch blocks when working with streams. And in the finally block, we need to actually close the stream. The input stream and output stream are closed in the finally block. Okay, so this is a good programming practice which we need to follow in our code going forward. So let's see this program in action. So what I do is here is I have a file called sample.txt and I want to copy it into sample copy.txt. Okay, let's go to my folder. Here I am. I have sample.txt. The contents of the file are hello, how are you, welcome and thank you. Okay, so we want to copy this sample.txt to another file called sample copy.txt. Let us run this program. Okay, so here we have sample copy. Yes, sample copy is the same as the sample. So we have sample.txt here and sample copy.txt here. You'll see that the contents are the same. So we copied a file using C#. Okay. So that was the first example. So let's continue. Next we look at buffered streams. We know that an operating system, for every IO operation, causes an interrupt on the system. Whenever an IO request happens from a program, like a read or a write to a file system, the process has to suspend its execution and hand over the state to the operating system. The operating system then reads data from a location or writes data to the location. For example, let's say you wrote your C# program and then you compiled it and you executed it. When your program executes, it becomes a process. Each process has a specific area on the heap which it can access, which it is licensed to access. Different processes have different distinct areas on the heap. Every program is a process. Your printer device program, for example, is also a process. So if you look at your computer and if you go to your task manager and you'll see a number of processes which are executing. Okay, all of these processes have specific areas on the heap memory which they alone are licensed to access. Process A or process P1 cannot access the memory of another process. In this case, if you look at this example, P1 is licensed and legal. It's legal for P1 to access the memory area M1, but it is illegal for P1 to access memory area M2 because M2 belongs to the process P2. Whenever P1 tries to access an area of the memory beyond its valid licensed area, we get a system fault. Okay, so the heap memory and the file system are two distinct aspects in the system architecture. Okay, let's say your program P1, the process it executes as a program, wants to read a file from the file system. So whenever the read is executed, the actual data resides in the file system. So it is not available in M1. So your process requests the operating system to read data for you by causing an interrupt. What the operating system does is it suspends your process, reads the file system, copies the contents of that file to memory area M1 and wakes up your program and saying that, hey, I got data ready for you. And as you continue to read byte by byte, each time the interrupt happens and the operating system reads a byte and puts it into the memory area M1 so that your process P1 can continue to read from it. So this is the general computer system architecture based on interrupts. This transfer of control between the process and operating system for every IO operation causes a strain on the processor, thereby reducing resources for the concurrent processes. If the processor is very busy processing your requests, then how will it have time for the other processes that needs its resources? Okay, remember your program alone does not execute in isolation. It is a concurrent process with other processes, right? And it is not fair on our part to exclusively control the operating system's resources. To solve the problem of too many reads and too many interrupts, the C# language provides an abstraction in the form of buffered streams. When you use buffered streams, we don't read data in bytes, but we read or write data in blocks. A block is composed of 512 bytes. So how to use buffered streams? We wrap the underlying stream into a buffered stream. That is all, right? And when you use buffered streams, when a read happens on a buffered stream, a block of data is read in ahead, causing the next byte, next read, to read from the internal buffer, not from the operating system interrupt. Okay, so when you say read, when using buffer streams, it not only reads 1 byte for you, but is very smart and reads a minimum of 512 bytes. Okay. So the next read does not actually go to the operating system, but continues to give from the internal cache. So this way the number of interrupts get reduced. Similarly, let's say you're writing to a file system. You don't write 1 byte at a time, because writing 1 byte at a time will cause a huge number of interrupts on the operating system, which is a very expensive operation. So what we do is, we keep on, when using buffer stream, the data is written to an internal buffer and physically moved to the device only when the byte count crosses 512 bytes. So data is written in, for write, data is written in blocks. Remember, however, when writing data to a buffer stream, we may reach the end of the file before we cross 512 bytes. So for this, we need to flush the remaining bytes to the stream. So always end your buffer stream write with a flush, so that any remaining bytes are flushed to the final output stream. Okay. The flush method performs a physical write of the remaining bytes in the internal buffer. Okay. So very simple. Let's look at the same example, the previous example we saw for copying a file. We have a source and a destination file, okay, and we get the streams from the open read for input and open write for output. Now, if you want to have a buffered stream, we just wrap the input stream onto a buffered stream. We create a new buffered stream and pass in the input stream. Similar to have a buffer output stream, we pass the output stream to the buffered streams constructor. That's it, and we have buffered streams. Everything else is the same like the previous example, except for the creation of the buffered streams. Now here what happens is, whenever we do a read, data is read ahead for us. Not only is not read byte by byte, but it is read ahead for us. And similarly, when you do a write, data is stored into an internal buffer and written to the file system only when it crosses that threshold. The minimum threshold is 512 bytes. And once we have done writing all the data to output stream, to the buffer output stream, the remaining data needs to be flushed. So we do that using the flush method on the buffer output stream. And remember, finally, to close the streams, the buffer input stream and the buffer output stream. One important note here, when using buffered streams, because optimization is already built into the C# code, it always falls back on buffered streams whenever it can. But as a programmer, it is always better to be explicit and use buffered streams whenever we can. Buffered streams are more sophisticated class than the normal streams class, and even support non-blocking I/O or asynchronous I/O, and are much feature rich when it comes to I/O programming. So the recommendation for you is to always use buffered stream wherever you can. Let's look at a quick demo again. Here we are at the method which copies files using buffered streams, right? So what we do here is, we first create a stream, input stream and output stream, using the open read and the open write method. Once we have the input stream and output stream, we create the buffered input stream and the buffer output stream. Okay, and after that, once we have the buffered streams, reading and writing the stream are just the same as in the previous example. We keep on reading bytes and then write them to the output stream, right? But what happens is, internally there is optimization built into the code. Whenever read happens, the operating system does a read ahead, and whenever write happens, operating system writes to internal buffer and only does a physical write to the file system when it crosses a certain threshold. And always remember to finally flush your buffer output stream. Okay, and in the finally block we close the streams. First the buffer input stream, the buffered stream, output stream, and then the input stream and the output stream. Okay. So very simple example. Let's run this again one more time. Here the first example, we copied a file. This is a normal copy to a file called sample.copy.txt. Then let's copy a file, the same sample.txt, to another destination, but this time let us use buffer streams. Let's execute this program. Okay, done. Let's look at our code and to see. Here we are, sample copy. Let's open it in TextPad. Here is sample copy 2, which is the same as sample. Okay. So here we actually copied the file using buffered streams. So let's continue working with text files. For text-based I/O, C# provides us the stream reader, the stream writer class. So if you're going to create text files or going to read text files, it is recommended to use the stream writer or the stream reader. Okay. To get a stream writer, there are two ways to do it. If you're creating a new file, use the create text method, or if you're appending to an existing file, use a stream writer on the existing file. For example, we have this file called sample.txt, right? And if you want to add text to this file, what I do is I first check if the file exists. If the file already exists, then we use the stream writer constructor. If the file does not exist, we create the file using the create text method. The create text method returns as the stream writer. Okay. So let us look at an example of a program that reads input from the keyboard and stores it in a file called sample.txt. All the text that's entered by the user is stored in the file until the user presses done. Okay. So we're going to run this program and ask the user to type whatever they want. Whatever they type in is stored in the text file called sample.txt. We keep on doing this with the user input until the user types DONE and presses the enter. Right? If you look at the source for this program, it's again pretty straightforward. We first have a file info object called for sample.txt. We check if the file exists. We need a stream writer, so we either use the create text or if it's an existing file, we actually get the stream on that file. So I first check if the file exists. If file exists, we use the stream writer constructor to get the right stream writer for the file. If the file does not exist, we create the file using the create text method, which gives us a stream writer. Okay. So what do? We do a console.readline. So we read text from the keyboard, and whatever text is entered by the user, we write it to the file using the writeLine method. Okay, and we do this until the user enters done. To read text from the existing file, we use the stream reader as shown below. Stream reader equal to new stream reader for a given path, and then we keep on reading lines until we encounter null. Okay, reader or read line until not equal to null. Okay, so what does the text files give us? So what is great about this text files, right? The stream reader and the stream writer provide abstraction for us in the form of the newline character. They actually provide methods to read and write lines of data from a file system. Okay. The newline character has different implementations in different programming languages and platforms. Some platforms use line feed and carriage return as the new line character, while some platforms use only carriage return to denote the end of the file. For example, let us say you're reading a file that was created in Linux, okay, and the user had entered the different lines using the enter key on that particular system. How the line feed, the new line character, is represented in the Linux operating system, we need not bother about it. Okay, when we read the program on the Windows operating system, the C# language, if you use the stream reader and the stream writer, the new line character is abstracted for us. Whatever new line character was used by the default native operating system where the file was created is transparently handled for us, so that we need not worry about whether it was line feed or carriage return, or only carriage return, or some other combination. Okay, so this is the abstraction that is provided by the text files, stream reader and the stream writer classes. Let us see a quick demo here. So we have this method, store input from keyboard, right? We just pass in a file name, and what we do is we check if the file exists. If the file exists, well and good, we get the stream writer on the file. If the file does not exist, we create the file and get a stream writer on that file. Ultimately, existing file or a new file, we get a stream reader, stream writer. Once we get the stream writer, we read input from the console and we write the text entered by the user into the file. Okay, we keep on doing this until the user enters done. Okay, and here is another example to copy a text file. So what we do is, again, we need a stream reader and a stream writer. From the reader we read line, and to the stream writer we do a write line. And as in all good programming practices, we use a try catch block, and in the finally we close the different readers. Okay, so let us run this example. Okay, here am I at the program.cs file. Okay, I'm going to store the user input, which is going to be entered by the user in the given path c:\.io, and I'm going to call it user input.txt. And once the input from the keyboard is stored, I want to display the file. So I'm going to display the file using, again, text-based.io. I'm going to say user input.txt. Okay, see, this file user input.txt does not exist now. c:\.io, this file, the user input.txt, does not exist till now. Okay, so what is going to happen is the source file is going to be user input.txt, does not exist, the file does not exist, so we're going to do a create text method on the file. The create text method will create a text file and it will return me a writer, stream writer object. So let's run this program. Here am I now. Okay, I will say .NET IO programming rocks big time. Okay, I'm done. So I'm going to say done. Okay, so I'm printing the contents of the file. It says whatever I entered .IO programming rocks big time is printed. So let's look at the file system to see if the file was indeed created or not. Okay, let's go to my path .io. Oh yeah, here is the file. Let me open it. Wow, here it is. Whatever I entered from the console, it has been stored in the file using text-based I/O. I entered some new line characters. It has been transparently mapped for me, right? So when displaying the file, okay, I use the display file method. Okay, it reads the file line by line and prints it. Now, if this file had been created in a different operating system, and if the new line character here had been different, I would not worry. My same program would still print the file contents, reading it line by line. Okay, irrespective of which operating system or which platform it was created on. That is the beauty of I/O programming. Okay, let's continue with the learning. Working with primitive data. Now, primitive data again differs from operating system to operating system, platform to platform. Some platforms use, for example, for integer, some platforms use 2 bytes, some use 4 bytes. For a character, some use 1 byte, some use 2 bytes, depending on the encoding. So, .NET Framework and the C# language prevent us from worrying about all the fine details of how the actual representation was done in the operating system. Okay. In order to read and write primitive data to files, the .NET Framework provides us a binary reader and a binary writer class. Primitive data types are the integer, float, double, boolean, and string data types. So reading and writing primitive data types is handled specially in the C# language. For example, we use the binary reader and the binary writer to read and write primitive data types. For example, if I want to write primitive data, I will open the binary writer. Remember, we open the very first example, we open the stream, and then we use buffered streams. Then we use the stream reader and the stream writer. And now for primitive data, we are using binary writer and the binary reader. Okay. So the binary writer has the write method, which is overloaded. So in this example, I have a float, a string, an int, and a bool value. And I say binary writer dot write. I pass in a float value, or a string value, or an int value, or a boolean value. The write method knows how to write the particular primitive data that is passed to it because it is overloaded. Okay, in this example, when we pass the float value to the write method, it writes the float value to the underlying file stream. And to read primitive data, we use the binary reader. The binary reader has different methods for reading different type of primitive data. For example, on the same file, we do a file to open and we use the binary reader. Okay, don't use stream reader. Okay, now on the binary reader, use read single, read string, read int32, or read boolean to read the respective values you entered previously. Okay, read single will give you a float value, read string will give you a string value, int32, read int32 will give you a int value, and read boolean gives you the actual boolean value. Very important note, the data that is read using the binary reader should be in the same order as it was written. For example, using the binary writer, we wrote float, string, integer, and boolean. So when you read from the stream, it should be in the same order. You should read single, read string, read int32, and then read boolean. Failure to do this will lead to reading invalid values from the file system. Very important note. Let us look at a quick demo. Okay, so I have this class called appData. Okay, and I have a float int bool and a float string int in the bool properties. Okay, and then what I do is I have a method called store settings. what store setting does is it opens a file and writes and uses the binary writer to write the different primitive data types: float, string, int, and a boolean value. Then I do a close on the binary writer. Okay, if I want to read settings, what I do is I open the file using a binary reader. Okay, and then I read a single, string, int, and a boolean because it is written in that order, right? So let us run this program and see. Okay, here I am at Visual Studio, the main program.cs, and I create a new app data object. Okay, and then I do a display settings, I store the settings, and then do the read settings. Remember, app data stores the file contents in the path appsettings.dat. Okay, appsettings.dat does not exist till now in my path, which is c:.io. Okay, fine. So let's run this program and see. Okay, so we have about to store settings and then reading the data from the file. So about to store settings actually writes using the binary writer, and reading it of the file reads the values using the binary reader. Okay. So let us look at the file. Oh yeah, we got appsettings.dat. Okay, now this file, if I try to open it with a text editor, open, let's say I use TextPad or something else to open it. Okay, you can find that this is a binary file. Okay, this is not a text file. So if you look at the text file, you can't make any meaning out of it, but the program knows how to read the file. Okay, see, the program is reading the file, but we can read it from a text editor. So using primitive data types, the data is written in a specially encoded format which is not equal to text IO. Okay, please keep this very clear. Text IO using stream reader and stream writer is very much different from primitive data type IO using binary reader and a binary writer. Okay, so let us continue with the learning. We come to object serialization, right? We seem to be working only with objects, isn't it? Everything is an object for us. Now the question is, how do we persist the state of an object beyond its lifetime? We know that when we create an object, it lives in memory, and when a program terminates, the object also dies. Suppose I wanted to save the state of the object in the file system, for example, beyond the life of its object. Okay, C# provides us with a convenient way to store the state of any object and fetch back the state of any persisted object using object serialization techniques. How do we do object serialization? It's very simple. Let's say we have a student object called student, and we have some attributes set on the student. So the student has some state. What we do is we open a file stream, okay, and on that stream we open a file stream. Okay, we create a binary formatter class, and the binary formatter we do a serialize call on a given stream with a given object. Okay, so if you look at this example, we open a file using the file.open method. Okay, then the important thing is we create a new binary formatter and call a serialize method on the binary formatter and passed in the object and which stream to serialize. Okay, what to serialize? Student, where to serialize on the stream. This is about object serialization. And that is it. Our object is serialized. Now, if we want to read the state of the object, what we do is, we again open the file, seeing the file will open, and we get the stream associated with the file. We create a new binary formatter class, and then we just say deserialize the stream. Deserialize method will return us an object which was serialized into the stream. Since we know in this file student.dat, we put in a student object, we cast it back into a student, and then we say stream.close. It is as simple as that. However, one important point to remember is, every object you want to serialize, its class should be defined with the serializable attribute, should be marked with the serializable attribute. Okay, let's look at a quick demo again. Here I am at student.cs, the same student class we looked at previously. It has the name, age and admission number. Since I want to serialize it, I'm going to use the serializable attribute. Without this, I cannot serialize my objects. Okay. Okay, here I am at program.cs on the main method. I'm going to serialize the student object in the path, the given path here, and the file name is going to be student.dat. Okay, so what I do is I first create two students, S1 and S2. Again, Harry Potter and Ron Weasley, differing by name as well as the admission number. Next, we create a list of students, and we add S1 and S2 to the list. Okay, and here is just printing the contents of the list. Now what we do is, we do a file.open on student.dat. Okay, and on that stream, once we get a stream, we create a new binary formatter, and we just say serialize students in the stream SW. That is all. Just 4 lines of code to serialize a full array list. Okay, just these 4 lines of code to serialize your list. Okay, now when we want to read back from the serialized data, when we want to deserialize the data, what we do is, we again open a file stream on the same file. Okay, and then we create a binary formatter, and we just say deserialize this particular file stream. Since we wrote student list of students, we cast it back into a list of student object back. And just to make sure we got the list back, we are iterating through the list. Okay, so very simple, just 4 lines of code to serialize and another 4 lines of code to deserialize. So let's save this and run this program. By the way, before we run it, look at this class called look at this file called student.dat, right? Student.dat does not exist in my path yet. I don't have student.dat yet. So let's run this program and see. Okay, we have 2 students, Harry and Ron. We serialize the student data, and then we actually deserialize the student data back. Okay, let's look at the file system. Here we are at c:dot.io, and here is the student.dat. Again, this is a binary file. We can't open it with a text editor. Even if you open it with a text editor, it will not make sense to us. Right? Let's try to see what it contains. Oh my god. Okay. Alright. purely, we can't make sense out of it, but the C# class, the binary formatter, the deserialize method can deserialize the stream to a given object. Okay, so that was object serialization. Let's continue. Here is a summary of what we have seen so far. We saw what are streams and why we need them. We need streams because input-output devices are very varied and complicated and have very finer, minute details that interface with the device drivers and the actual hardware. We programmers are saved from having to deal with all these complexities by using streams. When we use streams, the C# language and the compiled intermediate language code and executed by the CLR, the actual translation between the stream to the device is taken care of by the common language runtime, and it's completely abstracted for us, and that is why we use streams. Okay. Why did we use buffered streams? Buffered streams are an optimization for the operating system. The buffered streams uses block-based I/O as opposed to byte-based I/O. So the number of interrupts on the operating systems is less, so that the operating system's resources are preserved and not become our monopoly just because we want to do a read a file. For text-based I/O, we use stream reader and stream writer because stream reader and stream writer provide an abstraction for the new line character. Different operating systems, different platforms, different languages represent the new line character differently. So we need not worry about a file created in a different operating system, say Linux or Unix or Solaris, whatever. Our program, if it reads a text file, will continue to read the text file even if it is created in a different operating system. So text-based I/O, stream reader and stream writer provide an abstraction for the new line character. And for primitive data types, we use the binary reader and the binary writer. Again, primitive data types like int, float, etc., the representation format varies from operating system to operating system and from platform to platform. So that abstraction of how the primitive data is represented by the underlying operating system is abstracted for us using the binary reader and the binary writer. Okay. Then we looked at object serialization. Object serialization allows us to store the state of the object beyond its lifetime, and the binary formatter class, when used on a stream, allows us to serialize an object as well as deserialize a stream to an object. So we come a long way today, and input programming is a very important part of programming as such. I hope you enjoyed it, and there is time for self-evaluation. Please go to self-evaluation questions in the tutorial text and also do the exercises. I hope you enjoyed this lesson. We'll see you soon.